You wake to an ordinary morning. Sunlight slips through the window and spreads across the floor. You reach for a lamp, flip the switch, and the room is suddenly illuminated. You look across the room, and there it is, the light reaching your eyes so quickly that there seems to be no journey at all. You don't see it traveling. You don't watch it cross the space between the lamp and your face. There is no visible delay, no moment where the light appears to hesitate before arriving. It simply seems to happen. And because you've experienced this thousands upon thousands of times, your brain barely notices it anymore. But look at this familiar moment differently. The light in front of you did not simply appear. It traveled. It crossed space. It moved from one place to another, carrying energy through the room before reaching your eyes and allowing you to see the objects around you. And suddenly, an ordinary room becomes something much stranger, because light doesn't just move quickly. It follows a rule so precise and so deeply woven into the structure of nature that changing your perspective can change what moving even means. You spent your entire life watching light arrive, but you've probably never had to think about what its journey actually means. That is where the mystery begins. Because once you stop treating light as something that simply appears, and start treating it as something that travels through the universe, another strange problem begins to emerge, and this is where the story becomes much harder to explain. At first, the answer seems obvious. Maybe we simply haven't built an engine powerful enough, give a rocket more fuel, build a better propulsion system, develop more advanced technology. Perhaps someday we'll make something move faster and faster until we finally catch up with light. That sounds reasonable. But it misses the real problem. The limitation isn't simply that our machines are weak. It isn't a shortage of fuel waiting to be solved by better engineering. And light isn't merely an unusually fast thing that happens to be difficult to catch. Something much stranger is happening. The universe appears to impose a fundamental speed limit on the way information, matter, and cause and effect can move through space. And that raises a much deeper question. Why? Why should the universe care how fast something moves? Why should there be a particular boundary that nature refuses to let ordinary massive objects cross? This is where the story stops being about rockets and starts becoming about reality itself. And here's the surprising part. You don't need a particle accelerator to begin seeing the clues. You don't need to travel through space. You don't need an exotic experiment performed in some enormous laboratory. The first pieces are already sitting in front of you. Light, clocks, rulers, motion. Things you've encountered so many times that they feel completely ordinary. But when you put them together carefully, they begin revealing something deeply uncomfortable about our everyday understanding of space and time. And this is why simply saying, "nothing can go faster than light," doesn't really explain anything. It gives you the rule. It doesn't give you the reason. But before we explain the mechanism, there is something important to clear away. Because this subject has accumulated an enormous amount of bad science communication. There is a problem with the way relativity is usually explained. You hear, Einstein said nothing can go faster than light, or you would need infinite energy, or perhaps light is just really, really fast. And these statements aren't completely wrong. There are pieces of truth inside them. But they can leave you with the impression that relativity is nothing more than a strange rule someone discovered, and the universe simply decided to enforce. That isn't satisfying. Because if we're trying to understand physics, repeating the conclusion isn't the same thing as understanding the mechanism. And this is where a lot of popular explanations go off the rails. You see dramatic animations of clocks slowing down, rulers shrinking, astronauts aging differently, and grids bending through space. The images can be beautiful, they can even be useful, but sometimes the diagram becomes the explanation, and that's backwards. A picture showing space-time bending doesn't automatically tell you why space-time behaves that way. Saying that time slows down doesn't tell you what a clock is measuring, and saying that light represents the ultimate cosmic speed limit doesn't tell you why that limit exists in the first place. Even worse, relativity is sometimes wrapped in mystical language, as if Einstein somehow discovered that reality is an illusion and everything we experience is secretly meaningless. It isn't. The actual physics is stranger than that, but also more precise. So let's slow this down and earn the conclusion instead of announcing it. We're going to start with something almost painfully ordinary: motion and measurement. What does it actually mean to say that something is moving? How do you determine how far it traveled? How do you determine how long it took? And what happens when two observers, moving differently, perform those measurements? You don't need advanced mathematics to understand the central chain of reasoning. The mathematics eventually gives us Lorentz transformations, the invariant spacetime interval, and a precise relationship between energy and momentum. But you can understand why those ideas become necessary before touching the equations. That's the important distinction. We're not going to memorize the answer. We're going to follow the logic that forces the answer upon us. Because nothing can beat light because it requires infinite energy is only one consequence of a much deeper structure. As an object with mass approaches the universal speed limit, its energy and momentum don't behave according to ordinary Newtonian intuition. And underneath that behavior is something even more fundamental. Space and time themselves are connected in a way our everyday experience hides from us. That is the part worth understanding. Not the slogan, not the science fiction version, the mechanism. And once you understand that this story is about the mechanism rather than the slogan, the next step is surprisingly simple. Start with the question of what a measurement actually means. If you appreciate explanations that slow down long enough to actually show you how the pieces fit together, this is exactly what we're trying to do here. Science doesn't become more meaningful when we make it sound mysterious, and difficult ideas don't become easier by hiding the important parts behind jargon. The goal is simpler. Take an idea that seems impossibly complicated, follow the reasoning carefully, and let the strange conclusion emerge naturally. So, if that's the kind of science you enjoy, stay with us and explore the other explanations on this channel when you have the time. Now, back to the physics. Because before we can understand why light has such a peculiar status in the universe, we need to return to something much more familiar: motion. More specifically, what happens when two different observers measure the same moving object? That simple question is where everything begins. Imagine you're standing beside a railway track. A train moves past you at 80 kilometers per hour. Inside the train, someone walks toward the front at 5 kilometers per hour. From the passenger's perspective, they're moving at 5 kilometers per hour. But from your perspective beside the tracks, that passenger is moving at roughly 85 kilometers per hour. Nothing strange happened. The two velocities simply add. This is exactly what your everyday experience teaches you to expect from motion. If you're riding in a car and throw a ball forward, someone watching from the road sees the ball carrying both your car's motion and the ball's motion. For ordinary speeds, this works beautifully, and that creates a very natural expectation. If you move towards something that's already moving, shouldn't your measured speed of that thing increase? For light, the answer is no, and that is where the trouble begins. The speed of light in vacuum is exactly 299,792,458 meters per second. That number isn't merely a measurement we happen to like. Today, the meter itself is defined using that exact value. Sunlight takes about 8 minutes 20 seconds to travel from the sun to Earth. And when astronomers tell you that a star is 10 light years away, they're describing a distance, not a time. 1 light year is approximately 9.46 trillion kilometers. So light clearly travels. It takes time to cross enormous distances. But here's the remarkable part. If one inertial observer measures a beam of light moving through empty space, they measure that same invariant speed. Another inertial observer, moving relative to the first, does not simply apply the old train and passenger addition rule and obtain a different speed of light. Light refuses to cooperate with our ordinary intuition about adding velocities. Now, something has to give. Because we started with a seemingly harmless assumption that space and time behave the way everyday experience suggests. We imagine space as a fixed stage. We imagine time as a universal clock ticking identically everywhere. And we imagine motion as something that happens inside that stage. But if the speed of light is invariant for all inertial observers, those assumptions cannot all survive unchanged. This is the crucial pivot. Space and time have to participate in the transformation. And they do. One consequence is time dilation. A clock moving relative to you can accumulate less elapsed time between two events than a clock at rest relative to you. But be careful with the picture. The moving clock isn't malfunctioning. Nothing is physically breaking inside it. If you travel alongside that clock, you can consider it perfectly normal. Its ticking feels ordinary. Its mechanism behaves normally. The difference appears when observers in different states of motion compare measurements. Then there is length contraction. An object moving relative to you can be measured as shorter along its direction of motion than it is in its own rest frame. Again, the object isn't being crushed by some invisible cosmic pressure. Different observers are dividing the same space-time into space and time differently. And that leads to perhaps the strangest consequence of all: relativity of simultaneity. Two events that you consider happening at the same time may not be simultaneous for another observer moving relative to you. This sounds absurd only because everyday speeds hide the effect. At the speeds of cars, airplanes, and even spacecraft, these differences are usually so tiny that ordinary physics works almost perfectly. But as velocity becomes a substantial fraction of the speed of light, the effects stop being negligible. And this is where the Lorentz factor becomes useful. You don't need to memorize its equation. Think of it as a number that tells you how strongly relativistic effects matter. At low speeds, it's almost exactly 1. As your velocity approaches the speed of light, it grows larger and larger. Closer still, it becomes enormous. And in the mathematical limit where velocity approaches c, the Lorentz factor approaches infinity. That one behavior tells us something profound about trying to accelerate a massive object all the way to light speed. The familiar statement is that it would require infinite energy. That's true as a limiting statement in special relativity. But it's important not to mistake that sentence for the deepest explanation. The infinite energy result comes from the relativistic relationships between energy, momentum, mass, and velocity. The deeper structure is space-time itself. For an object with non-zero rest mass, increasing its velocity towards c changes the relationship between the energy you supply and the velocity you gain. You can keep adding energy. You can keep accelerating. You can get closer and closer. But reaching c is not like reaching 100 kilometers per hour and simply adding another 10. The mathematics increasingly resists that interpretation. The boundary at c is fundamentally different from ordinary speed values. And this is why the phrase light speed barrier can be misleading if you picture an actual wall floating somewhere in space. There is no physical wall waiting ahead of your spacecraft. Instead, the geometry of space-time defines a boundary separating different kinds of possible motion. This brings us to one of the most powerful ideas in relativity: the light cone. Imagine an event, right here, right now. From that event, light can spread outward in every direction. Those possible paths form a cone in a diagram of space and time. Inside the future light cone are events that can, in principle, be reached by a slower-than-light object, or influenced by a causal signal from the original event. Inside the past light cone are events that could have influenced you. Outside those cones are events that are too far separated in space-time for a normal, slower-than-light signal to connect them. The light cone is therefore much more than a drawing. It represents causal structure. It tells you which events can potentially influence which other events. And suddenly the speed of light has a much deeper meaning. It's not merely the speed at which photons happen to travel. It's tied to the maximum speed at which causal influence can propagate through space-time. That is why the limit matters. Because if you could send a controllable signal faster than light, something stranger would happen. Consider two events separated far enough in space. For one observer, you might send the signal first and receive the response later. That seems perfectly normal. But under special relativity, if the signal travels faster than light, there can be another inertial frame in which the temporal order of those two events is reversed. The receiver can appear to receive the signal before the sender transmitted it, and with the right arrangement of observers and return signals, the problem can become much worse. You can construct scenarios where information appears to arrive before it was sent. Cause can appear to follow effect. That is the real reason faster-than-light signaling is such a serious problem in ordinary special relativity. The issue isn't simply that something is moving really, really fast. It's that space-time itself determines the causal order of events, and light marks the boundary of that causal structure. So the pieces have now begun to lock together. Motion is relative. Light's vacuum speed is invariant. Therefore, space and time cannot remain absolute. That produces time dilation, length contraction, and relativity of simultaneity. The Lorentz factor grows without bound as a massive object's speed approaches c. The energy required to reach c becomes unbounded, and the same space-time structure produces light cones that define the boundaries of causality. One thing forces the next. And this is where the common explanation begins to fail. Because if you think the problem is simply that we haven't built a fast enough machine, you are solving the wrong problem. It quotes, tempting to think we've simply reached the limit of our engineering. Maybe the engines aren't powerful enough. Maybe we need better fuel. Maybe future materials will let us build a spacecraft capable of pushing through the barrier. And honestly, that intuition makes sense. It's how almost every technological problem in human history has worked. If something is too slow, build a better engine. If it can't carry enough, build a stronger machine. If you need more power, find a larger energy source. So when someone says, we can't travel at the speed of light, the natural response is, not yet. But relativity is telling us something very different. The problem isn't simply that our rockets are inadequate. Imagine taking a massive spacecraft and continuously adding energy to it. At first, the results look familiar. More energy produces more speed. But as the spacecraft gets faster, relativistic effects become increasingly important. You can keep supplying energy. You can keep increasing the spacecraft's energy and momentum. But the increase in velocity becomes smaller and smaller as the spacecraft approaches c. The closer you get, the more extreme the energy requirement becomes. And in the limit, reaching the speed of light would require an unbounded amount of energy for an object with non-zero rest mass. So adding more fuel doesn't eventually produce the missing final step. There isn't some secret quantity of gasoline waiting to push the spacecraft from 99.99999% of light speed to 199% of light speed to 100%. The mathematics doesn't give you that final step. And this is an important distinction. The universe isn't saying, your engine isn't strong enough. It's saying that the relationship between mass, energy, momentum, space, and time does not permit a massive object to simply cross that boundary. That's why calling it a technological limitation is incomplete. Technology determines how close we can practically get. Space-time determines what getting all the way there would mean. And suddenly the faster rocket idea looks different. It wasn't a stupid idea. It was simply based on Newtonian intuition being extended into a regime where that intuition no longer describes reality accurately. That's the part most simplified explanations leave out. They give you the conclusion, nothing can go faster than light, without showing you why building a stronger machine doesn't change the underlying rules. The deeper obstacle isn't sitting inside the engine. It is built into the structure of motion itself. So if the phrase, nothing can travel faster than light, is really shorthand for something deeper, what exactly have we been misunderstanding? Most of us learned a simple sentence, nothing can travel faster than light. And as a first introduction to relativity, that's useful. But taken literally, it can hide more than it reveals. The statement comes from the structure of special relativity, developed by Albert Einstein in 1905, when he showed that our ordinary assumptions about time, simultaneity, and motion could not all remain absolute. The result was a new picture of space and time connected by the Lorentz transformations. But here's where the familiar slogan needs some careful unpacking. When physicists talk about the light speed limit, they're not simply saying that photons happen to be the fastest objects nature has produced. The deeper statement concerns the local propagation of matter, energy, and usable information through spacetime. And there are important subtleties. For example, in an expanding universe, extremely distant galaxies can have recession rates greater than c relative to us. That doesn't mean those galaxies are locally flying through space faster than light. It's a consequence of the expansion of spacetime itself. That's very different from sending a spacecraft or information locally through space faster than light. And then there are hypothetical ideas in physics that can produce mathematical possibilities involving faster-than-light motion or unusual spacetime geometries. Those are interesting to study, but a mathematical possibility is not the same thing as experimentally established faster-than-light information transfer. No confirmed experiment has shown controllable information traveling locally faster than c. So here's the more precise way to think about it. Light is not merely a fast object. The speed c is woven into the causal structure of spacetime. In relativity, photons follow what are called null trajectories, paths through spacetime for which the spacetime interval is zero. Massive objects follow time-like trajectories. Those words may sound intimidating, but the idea is surprisingly simple. They describe fundamentally different geometric paths through spacetime. So the distinction isn't merely mechanical. It isn't that photons have exceptionally powerful engines. It's that light occupies a special place in the geometry of spacetime itself. And this is why you don't need to throw away the sentence you learned as a child. You weren't wrong. You were simply given the compressed version. Nothing can go faster than light is a useful shorthand. The deeper version is that c defines the boundary of causal influence in local spacetime. And this isn't merely philosophical. Modern technology has to account for relativity. GPS systems, for example, require relativistic corrections because clocks in different states of motion and gravitational environments do not accumulate time identically. Einstein's insight didn't stay inside a textbook. It became part of the machinery of modern civilization. And once you see the speed limit as a property of spacetime rather than a weakness of technology, the practical question becomes much clearer. What can we actually say about traveling close to light speed? So how should you think about all of this the next time you hear someone claim that they've discovered a way around the speed of light? You can use 4 simple rules. Rule 1. Ask what is actually moving. Is the claim about a massive object, a signal carrying information, or the expansion of space itself? Those are not the same thing. Rule 2. Ask whether we're talking locally or cosmologically. Local motion through spacetime follows the rules of special relativity. On enormous cosmological scales, the expansion of the universe can produce recession speeds greater than c without objects locally breaking the light speed limit. Rule 3. Ask whether usable information can actually be transmitted faster than c. Something appearing to move faster than light is not automatically evidence of faster-than-light communication. The real issue is whether cause and effect information can cross the causal boundary. Rule 4. Never confuse approaching c with crossing c. A massive object can, in principle, continue accelerating closer and closer to the speed of light. But as it does, the required energy rises dramatically. Relativistic effects become increasingly important, and its world line remains within the causal structure available to massive objects. Getting extremely close is one claim, crossing the boundary is another. And that distinction matters whenever you encounter sensational headlines about warp drives, superluminal particles, or breaking Einstein's limit. Now you have a mental model for separating the interesting physics from the misleading headline. And you can explain the central idea in one sentence. Nothing with rest mass can be accelerated through the light speed boundary, because c is not merely a speed limit imposed on objects, it is part of the causal structure of spacetime itself. That's the deeper answer hiding underneath the familiar slogan. The universe isn't simply refusing to build a faster rocket. The geometry of spacetime determines what kinds of motion and causal connection are possible in the first place. And now, return to that ordinary room where we began. Because the light reaching your eyes has just become something much stranger than it appeared. Now look at the room again. Sunlight crosses the window and reaches your eyes. A lamp illuminates the walls. Nothing appears unusual, but now you know what you're looking at. Every beam of light is moving through the causal structure of spacetime, obeying the same invariant constant that governs clocks, particles, astronomy, and communication. Every morning, every day, every time light reaches your eyes, the universe is quietly following the same rule. The ordinary world was never ordinary. And that is the kind of question worth carrying into the next ordinary thing you see. If this kind of explanation is useful to you, consider staying with the channel. We look at familiar things the way Feynman did, not just accepting the slogan, but asking what is really happening underneath the surface.